Hello everyone, this is Professor Theory. I'll be helping you to understand more about the topics in this video. Today, we're going to learn about the topic basic integration. Differentiation and integration are two main components of calculus. The easiest way to understand integration is that it is the opposite to differentiation. In arithmetic, the opposite to minus is plus, and the opposite to division is multiplication. And in the same way, integration is the opposite to differentiation. So let us derive the formula for integration. On the screen right now is the formula for differentiation. We will first revisit derivative and we will define how antiderivative looks like. For a start, we want to differentiate this equation. Individually differentiate each term will give us this: dy dx is equal to minus x plus 2. This is what we normally refer to as gradient function because it is an expression of gradient on the curve y. As an antiderivative, if we integrate the gradient function, we should get back the expression of y. If we look at this graphically, this is how the function y looks like. And if we integrate that function, we get the gradient function. And if we integrate the gradient function, we should get back the original curve on the left. That is almost too easy, but let us go into the detail. This is the formula for derivative again, and we want to come up with the formula for antiderivative, and we do not know how it looks like yet. So we start off by reversing the differentiation formula. So what I did is just take the left part of the differentiation formula, move it to the right, and the right part, move it to the left. It is not perfect, but a good start. The exponent is an expression of n minus 1. We want to get rid of that minus 1, so I'm going to do something really strange. It might defy some laws of mathematics, but before that, I'm changing the color of n to become red, and then assigning n plus 1 to equal the red n. So, essentially, all instances of n in that equation, I'm changing that to become n plus 1. So those in brackets were the old n, the red n. Now I have changed that to become n plus 1. And that is done for a good reason. Look at the exponent on the left. It is n plus 1 minus 1. So I managed to get rid of minus 1. So this is how the equation looks like now. But it's still not good because we still have the coefficient of n plus 1 on the left. So what we need to do is to multiply both sides of the equation by 1 over n plus 1. By doing that, we manage to cancel off n plus 1 on the left. So finally, we have the formula for integration. Well, not quite. I tell you why. Nevertheless, I'm putting the incomplete integration formula there, and we will perform differentiation and integration of the previous function. On the left is the differentiation, and now we want to integrate the gradient function so that we can get back the original function. By applying the formula, we get this, and simplifying it, we get this. Now, compare our answer with that of the original function. Are they the same? Do we get back our original function? No, not really. We miss the number 3. The reason for that is when we differentiate 3, we get the result of 0. And of course, when we integrate 0, we cannot get back the number 3. Because we cannot integrate 0 to become 3. We need more information if we want to find out the value of c. But for this moment, let's just add the c constant to our integration formula. And this is just to indicate that whenever we perform integration, there must be a constant there to be added. We can try to determine the value of c if more information is available, but for now, let's just update our integration formula. So that is a good one. We have completed deriving the formula for integration. Let us revisit the curve again and perform integration of the gradient function. So this is what we get. And notice that we have c right now. But do you notice that there is an information on the graph that we can use to determine the value of c? Yes, the curve intersects the y-axis at the coordinate of 0, 3. So we can use the information to determine c. So let's just assign whenever x is equal to 0, y is equal to 3. So by substituting the value for x and y, then we get the value of c, and c is equal to 3. So now we get back our original function. As a conclusion, we can say that differentiation is a process to turn the function of the curve to become the gradient function, and integration is the reverse process by turning the gradient function to become the original function of the curve. Now we want to look into definite integral and the area below the curve. On the screen right now, we have a simple parabolic function y is equal to x squared, and we want to determine the value of the area under the curve, which is indicated by a. Now we want to look into definite integral and the area below the curve. On the screen right now, we have a simple parabolic function y is equal to x squared, and we want to find out the area below that curve between x equal to 0 and x equal to 1, and we name it as a. We will approximate the area below the curve by dividing it into a number of rectangles. We will try to approximate the area by dividing the area into multiple rectangles. This is how early mathematicians define integration. At this juncture, we know that the area below the curve is smaller than that 1 by 1 square over there. So the range of the area must be between 0 and 1 unit square. Say that we divide the area under the curve into 4 equal width rectangles like this. So the width of the rectangle must be 1/4. Using the equation of the curve, we can figure out the height of each rectangle through these coordinates. Because area of rectangles is base times height, then the total area of the 4 rectangles can be calculated, and that is equal to 0.46875 unit square. As you might have noticed, that is not the right answer for the area below the curve, because there are extra areas protruding out above the curve that is shown in red. So the number that I've come up just now is just a very rough estimation, but we can improve on that estimation if we make the width of the rectangle to be narrower and increase the number of rectangles. We will try with 10 equally width rectangles. With 10 equally width rectangle, then the width of rectangle, or delta x, has become 1/10. We can repeat the calculation to find out the total areas of the 10 rectangles, but I'm not going to do it here for the interest of time, and I will just show you the results there. And as shown in the table, the number has got a little bit smaller, and the extra areas protruding above the curve has also reduced significantly. From the look at the diagram, we can figure out that the actual result is smaller than that number. So it is still just an estimation. But nevertheless, we have improved on that estimation. So we can try with ever-increasing number of rectangles to improve on that estimation. So on the screen right now is an estimated total area with 101,000 rectangles. It seems like the number is converging to a familiar value. So if we put infinite number of rectangles, then the answer will be 0.3333 endlessly, or in fractional format it is 1/3, and that is the right answer for the area under the curve. In mathematical form, we can write the summation of infinite number of rectangles to be like this. Fx is the height of the rectangle, and delta x is the width. Multiplying these two numbers will give us the area of each of the rectangles. And this is the summation of the rectangle, or summation of the areas of rectangles from rectangle number 1 up to infinity, with the condition that the width of each rectangle is approaching 0. And this is how it looks like in definite integral format for the function y equal to x squared. And in general, if we have a curve fx and we want to find out the area below the curve between x equal to a and x equal to b, then we perform definite integral of that function within that boundary condition of x equal to a and x equal to b. And it is called definite integral because of that boundary condition. And I will show a simple example on how to apply definite integral to find out the area below a curve. You should be familiar with this curve already, and we want to find out the area below the curve between x equal to 1 and x equal to 4. We will first integrate the expression using the integration formula, and now we put the expression inside the square bracket with the boundary condition of 4 and 1 outside of the square bracket. And this is what we do with it. We're going to replace the value of x with those boundary conditions, the upper boundary first. And this is how it looks like. Notice the number 4 in blue, that's the upper boundary. And then minus what? Minus that expression with the lower boundary condition, like that. So by simplifying each of the expression into the square bracket, we get this. And executing the minus, we get the value of the area between x equal to 1 and x equal to 4, and that is equal to 13.5 units squared. And note also that constant c has disappeared. Why is that? Because c exists in the left square bracket and also on the right, and after the minus, c disappeared. Well, when we are doing definite integral, it is not required for us to put the constant c. C is only relevant for indefinite integral. Calculus is one of my favorite branches of mathematics, and I hope it is so for you too. It has taught me to look into things in different perspectives. Thank you for your time and interest. Make sure you watch another video so that you can get more knowledge in mathematics. See ya!